So we'll start by downloading requisite Python libraries. In particular, this library, matplotlib.patches, will be imported as patches to draw a square and a circle. So let's get started. I'll initialize a figure. So first attempt is to draw these squares and circle. So that's how I'm going to initialize my figure, and then I'm going to set my x and y axis equal. So my aspect is going to be equal. And then I'm going to create a red square. So let's make a square, and that will be using patches dot rectangle. So I'll start with the left bottom coordinate of the rectangle. My left bottom coordinate of the rectangle is at -1, -1. The length is 2, the breadth is 2, and I want this square in a red color. So that's how this patch will get created, and I'll add it to my figure. So I'm going to run this, and here we are. So my leftmost corner is -1, -1. I have given some margins here, some white space, so that you can clearly see the red square. And on top of it, now I'm going to build a square, a circle, sorry. So circle will be exactly the same thing, patches dot circle. So I have to specify my origin of the circle, which will be 0, 0, and the radius of my circle, which is going to be 1. Then my face color will be none, and my edge color of the circle will be, let's say, blue, and line width will be 2. And now I'm going to add this to my figure. So there we are. Now we have a circle which is centered at 0, 0. Its radius is 1, and it is completely on top of the square. So square has a length of 2, as you can see it, and breadth of 2, and the circle has a radius of 1. So that's our A. And now we define how many number of random points we want to generate. So let's start with a small number, let's say 10. And we will pull out these 10 random numbers from uniform distribution. So how we are going to do it, we'll call it random points, rand points. And we are going to pull it out from uniform distribution. So it says what is the lowest value of the number, lowest bound of the number, random number. So I'll start with -1. It will go up to 1. And I want the size, because I want both x and y coordinate. So I want the random number to have 2 columns. First column will be x, and the second column will be y. That is depicted by this 2. And how many number of rows we need? As many number of points that we want to generate. So the coordinate of random coordinates of my point will be x and y, which is given by this. And I want to generate n, that is 10 points, 10 such points in the data. So let me see the maximum and minimum of this. So if I do this, so here we are, the maximum random point, positive random point is plus 0.831, and I can also do the minimum. So minimum is minus 0.9, maximum is plus 0.9, so it's working fine. In fact, we can see all the random points if we want to. So we can do this. So here you see that we have these 10 numbers, each having an x coordinate and a y coordinate, which is being randomly generated. So far so good. We are just going to disable these print statements. Now we can actually do a scatter plot of all these random points to see how they look. So I'm going to first extract the x coordinate, which is the first column. So rand points and all the rows and the first column, and then rand points, all the rows, and second column, which is y. And let's have a look. So here we are. You can see that there are 10 random points inside the square, and some of them are falling within the circle. So when we increase this, we see large number of points, and a few of them are falling within the circle as well. So I'm going to disable this now, and the idea here is to figure out a way in which we can identify points which are falling in this circle. So how we are going to do it is we are going to calculate the magnitude of each and every point from the origin, and how that can be done is using the formula that I showed earlier in PowerPoint slides, which is the square of x and square of y whole square root. That gives the magnitude. So we're going to do that. Let's call it norm of the points. Norm is the magnitude. So what we're going to do is we are going to extract the x value. So all the rows and the first column, which is the x value. So x square, so this is how x square will be implemented. Adding with it is rand points, all the rows, and the first column, which is y, and square of it. So this entire thing will then be under the square root. So this is how we're going to calculate it. So this will give us the magnitude of each and every point. Basically, this is x square and this is y square, and this should work. Let me just run the code to see if there's an error. So we have missed a comma here. Yeah, it's working fine. So now we are going to identify points whose norm is less than 1, which means these are the points which are going to fall in circle. So let's say points within circle. That will be all the random points which are obeying this rule, that is norm of points, which is the magnitude, is less than or equal to 1. That's the radius of a circle. So if the magnitude is less than 1, they are all going to fall within the circle. And we can actually cross check that. We can just copy this command and use this. So instead of rand points, we have points in. Let's run this. So clearly all the points which are within the circle have got plotted, and we will use the same logic to paint the point or to plot the points which are outside the. So here I'm going to call it points out, and now this relationship will flip, and these are all points out, x and y coordinates of points out. And let me plot this. So points out, and this relationship is wrong. This should be greater than 1. And now you can see some points. In fact, let me just disable points in first. So if I run this, now you can see all the points which are outside the circle. So this way we can build this whole thing. In fact, I'll just copy all these scatter plots and put them here. Points in, and let me just disable them, and points out. And in fact, we can give them some color. So here in this case, I'm going to give it a color, let's say black, and let's define its size to be 2, and let's do it for the remaining. Let's this be or let this be green, and let this be blue, or this can be green and this can be black. So let me just run it again. So here we are. You can clearly see that the blue points are outside the circle and black ones are inside. So finally, let's calculate the estimated value of pi. So this is nothing but, as shown in the PowerPoint slide, 4 multiplied by the length of the number of points that have fallen inside the circle representing its area. So basically points in divided by total number of points. And let's print the result. So the Monte Carlo estimation of pi is equals estimated value of pi, real value of pi is equal to. Alright, so let's see what happens here. So there we are. Since we have very few points, we have just about 100 points here, which is a very small number. So our estimation of pi is 3.08, whereas the real value of pi is 3.14. So as you can clearly see that we need to improve this accuracy. So let's increase the number of points to 1000 and run the same code again. So now we are accurate to the first decimal place, and you can see now that there are a large number of points which are falling within the circle, and hence the area estimation is better. We can do it better. We can increase the number of points to 10,000, and now you see that the estimated value of pi has slowly started converging to 3.14, and you see that the area, the points inside the circle are they have almost covered up the entire area of the circle. The entire red color area has become black. So let's further increase it, and there you are. Now all this entire area of circle is covered by red color is covered by black points. So the accuracy has improved quite a bit in comparison to what the real value of pi is. So this is in this nutshell is the Monte Carlo method. It is a very powerful technique for cases where mathematical analysis is not possible, or the underlying data distribution is not known, or there are too many complications in deriving the theoretical value of the complex event. So these techniques are used there, and they are very powerful and give very good results.